We're going to talk about calculating pH. pH you've all heard of. You've seen lifeguards use it at the pool. You may have tested your own pool or your hot tub with it. It indicates an acid or a base. It indicates acidity or basicity. Basicity. That sounds right. This property can be measured using a pH probe or with an indicator. But what does it mean? Okay, what are we going to do? All right, if you look at this data table, you'll notice we have 10 beakers. Each one has a different molarity. Remember, molarity is concentration. So we have a concentration of 0.1 molar hydrochloric acid, 0.001 molar hydrochloric acid, 0.00001, so on and so forth. Also, we have a column that has H3O in it. This is called the hydronium ion. Ooh, I didn't. Oops. This is called the hydronium ion, which is just water. And because water is polar, it has that attraction. It picks up an extra hydrogen from the hydrochloric acid. Okay, so this is called the hydronium ion. We have a column that has the concentration of the hydroxide ion, and then we have another column where we're going to multiply those two together. Okay, so I just told you this symbol means you have a water molecule that has picked up a hydrogen ion. So it's now got an oxygen bonded to two hydrogens, and then there's a third hydrogen that's attracted to the negative part of the oxygen. Beaker 2, which is a higher concentration. We're looking at 10 to the negative third versus 10 to the negative 11th. Well, I don't know about you, but I happen to know that the hydronium ion is higher because it's only 0.001 if we change the decimal, the scientific notation, and this guy is 0.000 with a whole bunch of zeros, 10 zeros plus, and then 1. So hydronium has a higher concentration. How do we calculate that concentration? We're looking at beaker 3. Well, here we have 0.00001. If I take that and convert it to scientific notation, I'm going to move it 1, 2, 3, 4, 5. I have 1.0 times 10. I moved it to the right, so it's negative fifth. Oh, look! It's the same number. So concentration, when you're talking about concentration scientific notation, it's the same as writing it like here. Only this we labeled with molarity. Well, this is also molarity. They're the same thing. They're just written in two different ways. Describe how the concentration of the hydroxide ion was calculated for beaker 8. What do you want to bet it's the same? Let's figure it out. 1, 2, 3, 1, 0. 1, 2, 3, 4, 1.0 times 10 to the negative fourth. We're looking at beaker 8. Oh yeah. The hydronium is 10 to the negative 10th. All right, that's not what we were calculating. AOH is 10 to the negative fourth. There you go. All right. So let's look. So first question, which is a higher concentration in an acid? If we go back here, here's our acids. Who has the higher concentration? The hydronium ion. Who's more concentrated in a neutral solution? Our neutrals are right here. They're equal. What's true for a basic solution? Our bases our hydroxide side is greater. Oops, no. So our hydroxide must be more than 10 to the negative 7th. The student makes the following statement on an exam. Acidic solutions contain hydronium ions, basic contains hydroxide ions. Is this true or false based on this information? Well, if we look, all of our acids they all have hydroxide in them, just not very much. Same thing with our bases. They all have hydronium ions in them, just not very much. So this is a false statement. Alright. Now it asks us to calculate the quantity of all these. So take a moment and do that. Hit pause. Come back when you're done. You should have discovered this times this is going to give you 1 times 10 to the negative 14th. This times this, 1 times 10 to the negative 14th. In fact, all of them are going to equal 1 times 10 to the negative 14th. So, if you know the hydronium ion concentration, can you figure out the hydroxide? Well, we just got done doing this. And every single one equaled 1 times 10 to the negative 14th. So, if we know hydronium, can we solve for hydroxide? Well, in math, we just divide both sides by hydronium. So 1 times 10 to the negative 14th divided by the hydronium concentration will give us the hydroxide. A solution has a hydroxide ion concentration of 10 to the negative third. What's the hydronium ion concentration? I'm sorry, I read it wrong. Hydroxide ion. What's the hydronium ion? Well, we'll take 1 times 10 to the negative 14th and we'll divide it by 1 times 10 to the negative third. This one's simple. You just subtract the exponents and we get 1 times 10 to the negative 11th hydronium ions. Would this be an acid or a base? Well, hydroxide is a fairly large number, so it's a base. It's a larger number than 10 to the negative 7th. This guy, a little bit harder to do, wants to know the hydronium ion concentration. So we're going to take 1 times 10 to the negative 14th, and we're going to divide by 4.79 times 10 to the negative 5th. Okay? So, let's see if I can do this. I have to turn it on first. Second E, negative 14, divided by, see what I've done? 4.79 second E, negative 5, 2.09 times 10 to the negative 10th. And that would be the hydronium ion concentration. Is the solution acidic, neutral, or basic? Well, that's a pretty small hydronium ion concentration, so we're going to go with basic. Now you got to teach yourself about logarithms. Okay? I'll give you my understanding. I taught myself all this the other day. We know that a logarithm is basically the opposite of something raised to a power. These are all going to be log-based 10s. Log base 10 of 1 is going to be equal to 10 to the 0 power, which is 1. Log base 10 of 10 is going to be equal to 10 to the first power, which is 10. I did this one wrong. 10 to the 0 would be 1. Oh, I just didn't write it in there. And the 1 was right here. Duh. Log to the base 10 of 100 is equal to 10 raised to the second power. 10 times 10 is 100. All right. So, I just explained logarithms to you, hopefully. You probably understand it way more than I do. I had to watch Professor Dave Explains, and then some other dude on the internet explain it to me before I finally was able to explain it to you. What would the logarithm of 1 million be? So if we have log of 1 million, it would be 10 times 10 times 10 times 10 times 10 times 10. It would be log 6. It would equal 6 of a million. All right, examples to verify it. You can do that on your own. Figure it out. Now, C, the number 250 is between 100 and 1,000. Okay? Explain why your calculator, let's do B first. Calculator to find the logarithm of 250. So, put in log 250. Too close? 2.39. Okay? And it says, this question says, why did it give us an answer between 2 and 3? 2.39. Well, because 2 would be 100 and 3 would be 1,000. So it's going to be some fraction of an exponent between the two. Okay? So let's estimate. 78,000 is going to be between 1,000 and 10,000, right? So it's going to probably be between 3 and 4. I'm going to guess 3.7. So I'm going to put in log 7,800. See, oops. Equals 3.89. Not a bad guess. So do the rest on your calculator, and then we'll start the video back up when you've all got it done, and you can check the work with me and compare to me. Alright, we're back. Anybody confused? Because I changed my shirt and my hair looks different? That's because I ran out of time yesterday, and I am finishing this on another day. So, now you know. Let's take a look at the data that you were supposed to just calculate. If you were going to estimate 0.0045, it's going to be between -1 and -2. The actual value is 1.3. 3.4 to the 10 to the -9th is between 9th and 10th, so it's 9. And the actual value is 9.5. 7.2 times 10 to the -4 will be between 3 and 4. The actual value is -3.4. All right, this page, we're going to do some more calculations with calculators. What is the difference in the way the first two columns express the data? One of them is your basic old-fashioned decimal point. The other is using scientific notation. Decimal notation versus scientific notation. The missing values for columns 1 and 2. Well, 10 to the -3rd, we would go 1, 2, 3.5. 0.001 molarity. For this guy, 1, 2, 3, 4, 1.0 times 10 to the negative fourth. Okay? Now, estimate the missing logarithms for B and E in Model 3. So that would be these two spaces here. So if we estimate 5.5 is going to be between negative 2 and negative 3, so it's going to be probably negative 2.5, we'll estimate. And this will be between negative 4 and negative 5. 2.7 will be, it's closer to the negative 4, so I'm going to go negative 4.2. Okay. Verify the answers using a calculator. So now we're going to plug it in. Log 5.5 second E, negative 3, negative 2.25. Okay, well, I was off. And of course, pH is the opposite. Notice the sign has changed. It's the negative log of the hydronium concentration. So the actual answer here, 2.25, I'll just round to two significant digits, 2.3. Okay, the actual answer for line E, 2.7, to take the log, 2.7, negative 5, and I get a negative 4. Obviously, I'm not very good at guessing these. Negative 4.6, which would make the pH 4.6. 19 says, given the examples in Model 3, write a sentence of mathematical equation that describes how to calculate the pH from the hydronium ion concentration. Well, basically, it's the negative log of the hydronium ion concentration. The missing pHs we just did. 21. Calculate the pH of a solution that has a hydronium concentration of 1 times 10 to the 8th. Alright, so if I put into my calculator log 1 EE8 to negative 8, I get negative 8. pH would be the negative of that, so it would be a pH of 8. Okay, this one will do the same thing. We'll take the log of 0.007. It's negative 2.15. So the pH is going to be 2.1. I'll call it 2.2. We'll do 2 sig figs. 2.2. Alright, next, discuss in your group how you would find the hydronium ion concentration in a solution if you were given the pH. Check your procedure using several examples from Model 3. So if you're given the pH, now you got to work backwards. If pH is the negative log of a concentration, in order to go backwards, we need to take the anti-log of the pH. Anti-log is the exponent. So what we're going to do, if pH is 6, we're going to make it negative 6, and we raise it to the 10th power, like I did here. Show you on a calculator. This calculator, of course, is the one, this is not my favorite, but I've made it negative 6, and then I've clicked power of 10, and it gave me 10 to the negative 6. 1, 2, 3, 4, 5, 6. On this calculator, what I'm going to do is I'm going to go second, 10 to the 6th, and it's, so here we go. And now I'm going to put negative 6 in with another parenthesis equals, I got the same answer. Alright, so same story for this. I'm going to do negative, let's clear it out, 5.43, and then if I click the little negative on this, and I didn't get the 43 in there, 5.43 negative 10, I get 3.71 times 10 to the negative 6. Okay, if I do it on my calculator, negative 5.43, 3.000003715. So, same thing. All right, very good. Thank you very much.